Hello all. In today's session, let me practice one more design example in your asynchronous sequential circuits. So in this sequential circuit, so for designing any asynchronous sequential circuit, we have to follow the design procedure. In the design procedure, first step is to draw the state diagram specifications based on your specifications, and then derive your primitive flow table. Then after that, we have to reduce the flow table using your merger table. So after that, we have to make sure to raise free the binary statement assignment. So thereafter, we have to see that any hazards are occurred or not in your given circuit. If it is not occurred, then we will move to your transition table. So then we will minimize your number of states which are used. So thereafter, we will design your logical diagram using your key map technique. So using an SR latch. So now they have given a specification to design a negative edge triggered T flip-flop. The circuit has T input and clock input like in the previous example. So we have here data input and as well as your gate input. Here they have mentioned it as a toggle input with a clock input and one output terminal. So the output state is complemented if toggle input is equal to 1 and the clock changes from 1 to 0. So since it is a negative edge triggered, so for a falling edge of your clock signal, your output of your state of your flip-flop is changing when t equal to 1. So we have to make sure that t input must be 1 and clock input is 0. So then the state will be complemented. If present state 0, output will give you logic 1. If present state is 1, output will give you the logical 0. If t is 0 and clock is 1, so there is no effect on your output. The previous state is continued as your next state. So otherwise, under all the input conditions, the output remains unchanged. So this must be, so we have to make sure to have your, so t must be equal to 1 and t equal to 1. So then clock is equal to 0. So then if present state is 0, output will be logic 1. If t equal to 1 and clock is equal to 0, so as our previous state is 1, so next output will be equal to logical 0. The other conditions which are t0, clock 0 or t is equal to 0, clock equal to 1 in such states of your inputs. So there was no possibility at the change in your next state. It will continue your previous state. So my previous state is 0, hence here. So though your clock is 0, so since t is 0, so we would obtain the next state is 0. Here t is 0, clock is 1, so next state is previous state only, which is here 0, no change in the state. So when t become 1 and clock is 0, it comes back to its initial state, which is here. So now it will move to your logical 1 state. So here we have mentioned that, so t is 1, clock is 0, first state. So we'll come back to your initial state. So like this, we have to draw your state table according to the given specification. So now we mentioned first initially your t input is 1. When t input is 1 and clock input is 1, initial output is 0. So next, when clock is moving to the negative edge, so since the toggle input is 1, your previous state is toggle to logical 1. Next, when clock is 1, t input is 1, so it may not be triggered. So when it is not triggered, previous state is continued as your next state. When toggle is 0, so previous state is 1. Next, t input is, since t input is 1, so output of your flip-flop will toggle to logical 0. Next, so we are following here the fundamental mode of operation. So only one input is changed on a single time. So now t input is 0 and clock is 0. Since t input is 0, so no change in the state, so previous state only, Next, toggle input 0. Now clock input is moved to the logical 1 state. So though it is moving to the positive raising edge, so since it is not clocked as well as toggle input is not changed, so previous state only continue. Next, if your clock input is 0 and your toggle input is 0, now for such state, my state B, so if it is following your the state of your fundamental, so now the previous state is 1 for B state, so only one input has to change. So hence here, so after B, so if you have obtained logical 1, so use your next state. Next, so clock is 1. When clock is 1, T input is 0. Output of your flip-flop is 1. So let I mention this state table. Using this state table, let me draw the primitive flow table. Now, so first we will find your state table, stable states. So now the stable state is achieved for your state A is on input condition 1 1. So toggle input and clock input. Here I mentioned here number of states which are derived from its asynchronous sequential circuit, which are total 8 states. Now here 1 1, your output is 0, is a stable state. So for a 1 1, so hence we circled here 1 1. And for such initial state of 1 1, the redundant state or your don't care state is 0 0. So hence we mention dashes. This is called as the redundant state. So which is not occurred because it is having the multiple input change. So two input bits must be changed. So two inputs, toggle input and clock input must be changed. So such input combination, your outputs are don't care. So hence we mention it as a don't cares. Next, for 0 1 input, so 0 1 input output, the next state which is from A is F with an output of 0. So hence here it is F. So but here I've not mentioned your output which is 0 since it is a unstable state. So in unstable state we can't specify your outputs. Next, for 1 0 input, so 1 0 input here after your initial state A, it will move to your B. So it is also unstable, so hence we are not mentioning their outputs. Next, coming to the B column, so B row, so here the state B is occurred on an input condition 1 0. So hence 1 0, state B is stable state, output is logical 1. And for such input 1 0, unstable state is or your invalid state is 0 1. So hence, so dashes. Next, for 0 0 input, so here G is your next state, output is don't care. Next, for 1 1 input, so your after your B, you obtain your C, so hence C dash. So like this, we have to write here all the values in your primitive flow table. Upon writing the primitive flow table, then we were going to draw the merger chart. In this merger chart, so your rows are having, so total 7 rows we have and with the 7 columns. Now A and C. So let me do that. So by compatibility we have to check up here each state. So A, C are compatible, A, B are compatible or not. Now see here the dashes are matching and here invalid. So G is there. So F here invalid. So A and C, B and B. So now so this B and B is matching. So if AC are equal, then these two AB states are compatible. So hence we have mentioned here AC if AC is compatible. Next A and C. So A and C dash dash matched, FH dash is matched, but here A is now outputs for 1 1 input of DC different outputs. So 0 1. So which is not compatible. So AC is not compatible. When AC is not compatible, AB also we won't have your AB states. So which are not compatible. So if A and C are compatible, then only AB is compatible. As here AC is not compatible, AB also not compatible. Next, in the same manner, you find for A and D. So A and D is possible if and only if BD are compatible. So BD are compatible, then only it will be A and E are compatible. A and F is 5 by compare. So now A and F, if I compare it, so F comma 0, here A comma, A is dash dash, where F is E comma dash, and F F, so A, so here dash. So both are compatible, so hence, so a tick mark is provided on this AG. So AG is compatible if and only if FH are compatible. So as here we have to check for FH. So we just wrote that if FH are compatible, then only it will be compatible. Next, A2H. So A2H. So dash and here dash dash G dash and FH1. So AC. So then B. So here two states must be equal. F must be compatible with H. A must be compatible with C. Then only AH are compatible. So hence we wrote it as FH must be compatible. So AC must be compatible. Then like this. So if I write it all the values. So now, so we obtain here AC is not compatible, BD is not compatible, FH is not compatible, along with AC are also not compatible. Only the compatible states are AF, BG, BGH. So BGH, BGH, and along with CH. Next, tick mark. So DFE or DEF, and then here EF. So we can also mention here EF. Next, F is different. So F is a maximal compatible table is only having F as well as their GH. So now let me draw the primitive cover table. So here cover diagram. So using this merging table, let me draw that. So A2. So now let me here which are compatible is, now let me write here as A is compatible with the tick mark one A comma F, and then so next one B is compatible with G along with H. Next we can have C is compatible with H. Next D is compatible with E, F. Next E is compatible with F. We have compatibility which is checked for F is an integral state, and G is compatible with H. Now if I write that covering diagram here, so now A, B, C, D, E, F, G, H. First let me combine here A, F, a line which is drawn from A to F, thereafter B to G, then B to G, G to H, C to H, thereafter so we have to draw for D, E, F, and then we have to draw for E, F, which is also included. F is different, so as here EF is AF is attached, so GH, so GH is also attached here, which can form a triangle. So we have total two triangles are available here, so which are here AF are only two state compatibility, and here DEF is here three state compatibility. GH or here BGH is here three state compatibility, and two state compatibilities C and H. So now the primary compatible maximal compatibility pairs are AF, BGH, CH, DEF. Now let me replace those here Karnaugh map with those possible ones. So AF, BGH, CH, and DEF. Instead of F, let I take here A, and instead of GH, let I take here B, and instead of H we will replace with C, and instead of EF we are going to replace with a D. Now here all E's are replaced with D, all G's are replaced with B, all H's are replaced with C, like that. So if I draw the table, so corner map table, we have the values like this. So with the alphabets, then we will replace that with your A with 0 0, B with the 1 1, C with 1 1, and D with 1 0 in order to avoid your logical race. So let me assign here the sequence of your inputs or the present state in your present state as well as your sequence of inputs in your binary or a sequence, I mean 1 bit change. So 0 0 0 1 1 1 0 binary formation or should have your unit distance. So hence we have mentioned 0 0 0 1 1 1 1 0 on both your inputs as well as your the present states. So now these are your present state values. So which are replaced the alphabets with your 0 0. A with 0 0, B is with 0 1, C is 1 1, and D is 1 0. So upon doing this, so now let me write for your output of your Q also. So now earlier diagram we have mentioned here a dash. So 0 0 here. So since it belongs to your 0, so we mentioned here 0. So it is 1 0. Is don't care for A input. So hence we have just marked this as a don't care here. And 0 1. So as here C is doesn't have your value, but on your left and right it is having the outputs 1. So hence it is also having the output function value is equal to logical 1. So next here, so first column doesn't have your first column value doesn't have your value, last one is also doesn't have, but the right and your left of these two are ones. So hence in your next table it will be mentioned as a 1 here in the first column, and here we will place your don't care. Next 0 zeros are the outputs of your class. As here left and right are 0, so hence the A output must be equal to also equal to 0. Now upon drawing that, so by using your state transition, using your toggle flip-flop, here present state is 0, next state of your capital Y1 is 1. So 0 1 is so set state which denotes here. So your SR flip-flop, we have to draw this is with the SR flip-flop. So SR flip-flop excitation table is small y1 and capital Y1. So if I am taking that as a 0 0, your SR inputs are it is equal to 0 don't care. So 0 1 is 1 0, 1 0 is 0 1, and 1 1 is it is don't care 0. So using this state transition table, so let me write your values of your S1, R1, S2 and R2. So using your state transition from small y1 to small y1 value is this as your input. So capital Y1 value is this. So small y2 and capital Y2. So 0 to 1 and 0 0. So 0 to 1 is 1 0 are my inputs. So 1 and R1 is 0. So next state is 0 0. So hence 0 don't care. So like that you have to write your all the values for your next transition table along with your outputs too. So now upon writing all these values, so then we can find your S2 as well as your R2 value. So if you minimize your equation, then you obtain S1 is equal to Y2 into TC plus Y2 bar into TC, as here we have only two pairs. Next R1 is equal to Y2 into T bar C bar plus Y2 bar into TC. So here also we have here two pairs. So next, and S2 is equal to 1 and don't care, one pair only by 1 bar into feedback from your capital Y1 is taken, and complementary one is taken, and that is connected to the T and C bar. So R2 is equal to Y1 into TC bar. So now, so using these expressions, we are going to draw the logical diagram here. So these two are your SR latch inputs. So S1 R1 and here S2 and R2. As S1 here it is equal to Y2 into TC plus Y2 bar into TC. So hence here we connected. So Y2 into TC. So Y2 into TC. So now T is connected, one of the input of this, and the input is coming from your C input, and this is coming from your output of your Y2. So hence first AND gate will give you the product of your TC into Y2. Second AND gate will give you the product of your, so as here it is connected with your, so T bar, and here C bar along with, so it is connected from Y2 bar, small Y2 bar. So here it is also equal to small y2. So these two are added using your AND gate. So hence we could have here the addition of your TC y2 plus here T bar into C bar into y2 bar. So like this, the first S1 output is derived into your logical diagram. The same manner we are going to have your R1 along with S2 as well as your R2 will give you the output where Q is equal to, so in the previous session we have here Q equal to Y2. So small y2 or present state will also like your output. So like this we have to design your circuit with a toggle flip-flop. So at the design of your with a given statement toggle flip-flop, output can change only when clock is equal to 0 and t equal to 1.